Download this code from codegive.com, link in the description below. OK, let's dive deep into the world of adaptive and non-adaptive routing algorithms in computer networks. This will be a comprehensive guide, covering concepts, differences, examples, and even some illustrative code snippets, primarily conceptual, as real-world routing implementations are complex. Introduction to routing and routing algorithms. What is routing? Routing is the process of selecting the best path for data packets to travel from a source to a destination across a network. It involves determining the optimal sequence of network devices, routers, switches, through which the packet should pass. The role of routing algorithms. Routing algorithms are the heart of the routing process. They are the software programs executed by routers that determine the paths. These algorithms use various metrics and information about the network topology to make these decisions. Goals of routing algorithms. Correctness. The algorithm should find valid paths to the destination. Simplicity. The algorithm should be easy to implement and maintain. Robustness. The algorithm should be able to handle network changes, link failures, congestion, and still find alternative paths. Stability. The algorithm should converge to a stable set of routes and avoid oscillations. Fairness. The algorithm should distribute traffic fairly among the available paths, avoiding congestion on certain links while others are underutilized. Optimality. The algorithm should find the best path according to some defined metric, example shortest path, least cost, highest bandwidth. 2. Adaptive versus non-adaptive routing, the core difference. The fundamental distinction between adaptive and non-adaptive routing lies in their response to network conditions. Non-adaptive routing, static routing. Also known as static routing or fixed routing. The routing decisions are predetermined and do not change in response to network conditions like traffic load or link failures. Routes are calculated once, typically by a network administrator, and then loaded into the router's routing tables. The routes remain static unless manually reconfigured. Advantages. Simple to implement. Low overhead, no continuous updates. Predictable behavior. Disadvantages. Inflexible. Poor performance during congestion or link failures. Not suitable for dynamic networks. Manual intervention required for updates. Examples. Static routing tables configured in small networks. Simple stub networks with a single connection to the internet. Flooding. Adaptive routing, dynamic routing. Also known as dynamic routing. Routing decisions dynamically adapt to changes in network conditions. Routers continuously gather information about the network, example link costs, congestion levels, and adjust their routing tables accordingly. The algorithm can choose different paths for different packets heading to the same destination based on the current network state. Advantages. Adaptable to network changes. Better performance under congestion and link failures. More resilient. Disadvantages. More complex to implement. Higher overhead, continuous updates and information exchange. Potential for instability, oscillations. Examples. Distance vector routing, example RIP, routing information protocol. Link state routing, example OSPF, open shortest path first, ISAs, intermediate system to intermediate system. Asterisk path vector routing, example BGP, border gateway protocol. 3. Detailed comparison table. Feature non-adaptive routing. Adaptive routing. Adaptability. No adaptation to network changes adapts dynamically to network changes. Route calculation predetermined, static dynamic, based on network state. Complexity simple more complex. Overhead low higher. Responsiveness slow to changes fast to changes. Suitability small, stable networks large, dynamic networks. Examples static routing, flooding RIP, OSPF, ISAs, BGP. Memory requirement low higher. CPU utilization low higher. Congestion response poor better. 4. Key adaptive routing algorithms, a closer look. Let's delve into some prominent adaptive routing algorithms. Asterisk distance vector routing asterisk. Asterisk each router maintains a distance vector, a table, containing the estimated distances, costs, to all other routers in the network. Asterisk routers periodically exchange their distance vectors with their directly connected neighbors. Asterisk upon receiving a distance vector, a router updates its own distance vector by calculating the shortest paths to all destinations using the Bellman-Ford algorithm. Asterisk example asterisk RIP, Routing Information Protocol. Asterisk how it works, conceptual. 1. Initialization asterisk each router knows the distance to its directly connected neighbors, usually 1, or a configured metric. Distance to all other routers is initially set to infinity. 2. Exchange asterisk routers send their distance vectors to their neighbors. 3. Update asterisk a router receives a distance vector from a neighbor. For each destination in the received vector, the router calculates the total cost to reach that destination via that neighbor, cost to neighbor plus neighbor's cost to destination. If this total cost is less than the router's current best estimate to that destination, the router updates its distance vector and forwarding table to use that neighbor as the next hop. 4. Repeat asterisk steps 2 and 3 are repeated periodically until the distance vectors converge, no more changes. Asterisk limitations asterisk. Asterisk count to infinity problem asterisk slow convergence in case of network changes, leading to routing loops. Triggered updates and split horizon can help mitigate this. Asterisk limited scalability. Asterisk conceptual Python-like code, illustrative. Asterisk explanation of the code asterisk. Asterisk distance vector router class represents a router. Asterisk initialize underscore distance underscore vector, initializes the distance vector. Distance to itself is 0, distance to neighbors is the direct cost, and distance to all other routers is infinity. Asterisk update underscore distance underscore vector, when a router receives a distance vector from a neighbor, it checks if going through that neighbor provides a shorter path to any destination. If so, it updates its own distance vector. Asterisk send underscore distance underscore vector, returns the router's current distance vector to be shared with neighbors. Asterisk the example creates 4 routers, A, B, C, D, with specified neighbors and costs. It then simulates multiple rounds of exchanging and updating distance vectors until the vectors converge, no more changes. Asterisk the updated flag is used to determine when the network converges. If after one exchange round, there is no update, this indicates convergence. Asterisk link state routing asterisk. Asterisk each router maintains a complete map of the network topology. Asterisk routers discover their neighbors and broadcast their link state information, example the status and cost of their links, to all other routers in the network. This is done using a reliable flooding mechanism. Asterisk each router then independently calculates the shortest paths to all destinations using an algorithm like Dijkstra's algorithm. Asterisk example asterisk OSPF, open shortest path first, is intermediate system to intermediate system. Asterisk how it works, conceptual. 1. Discovery asterisk routers discover their neighbors, routers directly connected to them, using a hello protocol. 2. Link state advertisements, LSAs. Each router creates an LSA describing its directly connected links, neighbors, cost to each neighbor. 3. Flooding asterisk routers flood, propagate, their LSAs to all other routers in the network. Reliable flooding mechanisms are used to ensure that all routers receive all LSAs. 4. Topology database asterisk each router builds an identical topology database containing all the LSAs received. This database represents a complete map of the network. 5. Shortest path calculation asterisk each router uses an algorithm like Dijkstra's algorithm to calculate the shortest paths from itself to all other routers in the network based on the topology database. 6. Routing table update asterisk the shortest paths are used to update the router's routing table. Asterisk advantages asterisk faster convergence than distance vector routing. Asterisk avoids count to infinity problems. Asterisk supports more complex metrics and features, example quality of service. Asterisk more scalable than distance vector routing. Asterisk disadvantages asterisk more complex to implement. Asterisk requires more memory and processing power due to the need to maintain a full topology database. Asterisk conceptual Python-like code, illustrative, Dijkstra's algorithm. Asterisk explanation of the code asterisk Dijkstra, graph, start, implements Dijkstra's algorithm to find the shortest paths from a starting node to all other nodes in a graph. Asterisk graph, represents the network topology as a dictionary. Each key is a node, router, and the value is another dictionary representing the node's neighbors and the cost to reach each neighbor. Asterisk distances, stores the shortest distances from the starting node to each node, initialized to infinity. Asterisk predecessors, stores the predecessor node for each node along the shortest path. Asterisk priority underscore queue, a priority queue is used to efficiently select the node with the smallest known distance to process next. Asterisk reconstruct underscore path, predecessors, start, and, reconstructs the shortest path from the starting node to a specified destination node based on the predecessors calculated by Dijkstra's algorithm. Asterisk path vector routing asterisk an extension of distance vector routing designed to avoid count to infinity problems and support policy routing. Asterisk instead of just advertising distances, routers advertise the entire path to a destination. Asterisk routers can use the path information to detect and prevent routing loops. They can also apply policies to select routes based on factors other than just distance. Asterisk example asterisk BGP, Border Gateway Protocol, used for routing between autonomous systems, ASs, on the Internet. Asterisk how it works, conceptual. 1. Path advertisement asterisk each router advertises the path it uses to reach a destination, rather than just the distance. The path is a sequence of AS numbers. 2. Path selection asterisk when a router receives multiple paths to the same destination, it selects the best path based on a set of policies and attributes, example path length, local preference, as path length, origin. 3. Loop detection asterisk if a router sees its own AS number in a received path, it knows that a loop exists and discards the path. Asterisk key features asterisk loop prevention. Asterisk policy-based routing. Asterisk interdomain routing, routing between different ASs. Asterisk BGP attributes asterisk BGP uses a number of attributes to influence path selection, including asterisk weight asterisk Cisco specific attribute, Highest weight is preferred. Asterisk local preference asterisk indicates the degree of preference for a path within an as. Higher is preferred. Asterisk as path length asterisk the number of as's through which a path travels. Shorter is preferred. Asterisk origin asterisk indicates the origin of the path, example IGP, EGP, incomplete. Asterisk MED, multi-exit discriminator used to influence traffic entering an as. Lower is preferred. Asterisk note asterisk implementing BGP from scratch is a very complex undertaking. The code below is a highly simplified representation to illustrate the path vector concept. Asterisk conceptual Python-like code, illustrative. Asterisk explanation of the code asterisk. Asterisk path vector router, represents a router in an autonomous system, as. Asterisk add underscore neighbor, adds a neighbor router, specified by as number, with a cost. Asterisk advertise underscore routes, simulates advertising routes to neighbors. In a real BGP implementation, policy rules would determine which routes are advertised to each neighbor. Asterisk receive underscore routes, simulates receiving routes from a neighbor and updating the routing table. It checks for loops, the router's own as number in the path, and applies policy rules. Asterisk apply underscore policy, a placeholder for complex routing policies that might modify route attributes. Asterisk compare underscore paths, compares two paths to the same destination based on various attributes, example path length, local preference, and selects the best path. Asterisk the example creates three as's, as 1, as 2, as 3, and simulates the exchange of routing information. V. Flooding, an example of non-adaptive routing. Asterisk how it works asterisk. Asterisk when a router receives a packet, it forwards the packet to all of its neighbors, except for the neighbor from which it received the packet. Asterisk each router continues to flood the packet until it reaches the destination. Asterisk sequence numbers are used to prevent packets from circulating indefinitely. A router keeps track of the sequence numbers of packets it has already seen and discards duplicates. Asterisk advantages asterisk. Asterisk simple to implement. Asterisk guaranteed to reach the destination, if a path exists. Asterisk robust, can handle link failures. Asterisk disadvantages asterisk. Asterisk inefficient, generates a large amount of traffic. Asterisk can lead to congestion and network overload. Asterisk use cases asterisk. Asterisk rarely used as a primary routing algorithm in large networks. Asterisk used in some specialized applications, such as asterisk reverse path flooding, RPF, in multicast routing asterisk used to determine which multicast packets to forward. Asterisk emergency broadcasting asterisk in situations where reliability is paramount and efficiency is less of a concern. Asterisk conceptual Python-like code, illustrative. Asterisk explanation of the code asterisk. Asterisk flooding router class, represents a router using flooding. Asterisk receive underscore packet, receives a packet and checks if it has already seen it, using seen underscore packets. If not, it floods the packet to all neighbors except the origin. Asterisk the dummy packet class is a basic class to represent a packet. It holds a unique ID, origin router, destination router, and data. Asterisk the example creates 4 routers and simulates flooding a packet from router A to router D. Asterisk the seen underscore packets dictionary prevents infinite loops by tracking which packets each router has already processed. 6. Factors to consider when choosing a routing algorithm. Asterisk network size and topology asterisk for small, stable networks, static routing might be sufficient. For large, dynamic networks, adaptive routing is essential. Asterisk network dynamics asterisk if the network topology and traffic patterns change frequently, adaptive routing is necessary. Asterisk traffic characteristics asterisk if traffic is predictable, static routing might be suitable. If traffic is bursty or unpredictable, adaptive routing is preferred. Asterisk performance requirements asterisk consider the desired performance metrics, example latency, throughput, reliability. Asterisk complexity asterisk balance the complexity of the algorithm with the available resources, processing power, memory. Asterisk administrative overhead asterisk consider the effort required to configure and maintain the routing algorithm. Asterisk security requirements asterisk some routing algorithms are more secure than others. Consider the security implications of the chosen algorithm. 7. Modern trends and considerations. Asterisk software-defined networking, SDN SDN separates the control plane, routing logic, from the data plane, packet forwarding. This allows for more flexible and centralized control of routing. SDN controllers can implement sophisticated routing policies based on real-time network conditions. This is a form of adaptive routing, but implemented in a centralized manner. Asterisk traffic engineering asterisk optimizing network performance by strategically controlling the flow of traffic. This can involve manipulating routing metrics or using explicit routing paths. Traffic engineering is often used in conjunction with adaptive routing. Asterisk machine learning, ML, for routing asterisk ML is being explored for use in routing to predict traffic patterns, detect anomalies, and optimize routing decisions. ML-based routing algorithms can adapt to network conditions more effectively than traditional algorithms. Asterisk segment routing asterisk a routing architecture that allows the source node to specify the complete path a packet should take through the network by encoding the path as a series of segments, labels, in the packet header. Segment routing can be used in conjunction with both adaptive and non-adaptive routing approaches. 8. Conclusion. Choosing the right routing algorithm depends on the specific requirements of the network. Non-adaptive routing is simple but inflexible, while adaptive routing is more complex but can adapt to changing network conditions. Understanding the trade-offs between these two approaches is crucial for designing and managing efficient and reliable computer networks. Remember that the code examples provided are simplified illustrations and real-world routing implementations are far more complex. The future of routing will likely involve a combination of adaptive and non-adaptive techniques, along with SDN, traffic engineering, and machine learning, to create more intelligent and efficient networks.